Now let's move on to second topic of today's lecture, which is the strain energy for general stress state. So when we consider general stress state, we have to first notify and notice that there is 6 independent stress state and 6 independent strain state. So strain energy density is given as U equals to be 1 over 2 sigma x epsilon x plus total 6 terms, because there are 6 pairs of independent stress and strain state. However, if you want to somehow do perform the strain energy density calculation that we have done in previous video, so we have to somehow rewrite the expression for U in terms of sigma square over 2e or e epsilon square. Okay, just for the convenience, mathematical convenience. So based on Hooke's law, if you get rid of all those strain terms and replace that with in terms of normal stress and shear stress, it turns out to be a little bit more complex term. Yeah, the reason why we have a little bit more complex expression if we get rid of the strain component is that epsilon x, epsilon y, and epsilon z, they are coupled with each other through the Poisson ratio. Okay, so because those normal stress component are coupled through the Poisson ratio, you have more terms related to normal stress. However, the terms related to shear stress, they stays as 3 terms. Okay, now instead of using general coordinate system, we can also use principal axis. Okay, so suppose that we have x, y, z coordinate system. However, after doing obtaining the principal axis ABC, at this ABC coordinate system, you're not gonna have any shear stress component. Then U becomes 1 over 2e sigma A square, sigma B square, sigma C square minus 2 nu and the cross term between these sigmas. Okay, so this is the strain energy density expression you can obtain for principal axis. Of course, strain energy density does not depend on the coordinate system, and what you can realize here is that if you learn the formal derivation of stress and strain energy in general 3D, you'll be able to prove that U here and U here is equal to each other. But we're not gonna give you the formal proof about it. However, this must be true. Like, for example, suppose that you are considering a beam under axial loading. Whether you take x, y coordinate, whether you take x prime, y prime coordinate, whether you take x double prime and y double prime coordinate, whatever coordinate you choose, strain energy density must be same. It's same as like when you solve the energy conservation problem in freshman physics. Depending on coordinate system, if your potential energy, kinetic energy changes, you cannot say that the physics law is correct, right? Same is here. What kind of coordinate system you choose, your answer must be coordinate independent. Okay, so please be aware about it. In addition to that, if I want to add like one more property about strain energy is that you can always divide the strain energy density into 2 parts: volume change part and distortion part. It's related to more like a shear. It's related to hydrostatic volume change. So let me give you like a more detailed discussion. So suppose that the average normal stress as 1/3 of sigma A, sigma B, and sigma C summation. Of course, I based on this relationship, even though you consider the principal axis, your strain energy density expression should be same as whatever coordinate system you choose. And given this principal axis, you only have the normal stress component, and this normal stress component, these 3 values can be different to each other. Then you can convert the sigma A into epsilon sigma bar plus sigma A plus, which this refers to the difference between sigma A and sigma bar, and you can do the same thing for sigma B and sigma C. Okay, so now based on superposition principle, you can couple decompose this into two problems. First problem and second problem. First one, you have exactly same stress on each planes, so you have only volume change and no shape change. For second one, you're gonna have different magnitude of sigma a plus, sigma a prime, sigma b prime, and sigma c prime, and here you expect no volume change and only shape change. Okay, so if you take out the strain energy density out of this sigma bar hydrostatic state, your expression will be something like this. If you plug in the expression for strain energy density, this guy, to the strain here, which is sigma c minus sigma bar, which is sigma a minus sigma bar, which is sigma b minus sigma bar, you're gonna end up deriving ud equals to be this expression 1/12g, summation of these three terms. Okay, so of course, if you use the relationship between the shear modulus and Young's modulus and Poisson ratio, one can show that U, which we derived here, can be written as UV plus UD, volumetric contribution of strain energy and distortive contribution of strain energy. Okay, so this is something I want to tell you regarding the general stress state and strain energy density. Okay, so please be aware that we can have strain energy density that does not depend on the coordinate system, and that strain energy can be decomposed into volume change term and distortion term, and how to separate these two by obtaining the average normal stress and considering the deviation from average normal stress for ABC component. Okay, so with that, let me finish the recording for the video of second topic.